Welcome everyone. I guess we have lots of people collecting the sandwiches. We just, today we're very fortunate to have two excellent talks on exoplanets. We heard the first one at the ITC Lunch by Leslie Rogers. She's sitting over there. And we learned a lot from that talk already. And we look forward to the second talk of today, the Bob Price lecture by Bekki Dawson, and many of you may remember from many years ago when she was here. And we very much look forward to her colloquium later today. We'll start with the big picture of the universe as a whole by Weinberger, the ITC postdoc, who will talk about well, I guess the first line is in French, is it? Or Latin. Latin, okay. Well, I don't know what it means, so I cannot read it. On yet it moves. Okay. The public version of the Arepo code. So I guess the reference is to the universe moving. And Bekki will talk about who did it, the British sculpting multi-planet systems. And then we'll hear from Leslie. She's visiting us from the University of Chicago. And she will talk about the joint mass radius period distribution of exoplanets. So it's three-dimensional, right? And finally, we'll hear from Trevor Rhone at the CFA, speaking about the machine learning studies of two-dimensional magnetic materials, and we look forward to that as well. Ryan.
Okay, thank you. Welcome, everyone. What I want to talk about today is, of course, I'm a computational cosmologist / galaxy formation person, but it's more technical in this case, and it's a project I've been working on for the last year or so in collaboration, well, mainly with Volker Springer and Rüdiger Packmer at MPA, and which is the public release of the Arepo code that Volker Springer wrote about a decade ago now. And we're now preparing a version that is publicly usable as opposed to the development version we had before, which was heavily experimental, largely undocumented, and essentially completely unusable for anyone who did not have supervision from one of the developers. So we're trying, or my job was to change this a bit, and I hope I succeeded. So before jumping to what the code is actually technically, let me briefly discuss what it actually does, the equations it solves. So on the largest scale, and we're talking here about 300 megaparsec on a side, the evolution of the matter density in the universe is governed by the expansion of space mainly, and as a kind of first order effect, so to speak, the gravitational interaction, in particular in terms of the dark matter. This can be described by a collisionless fluid using the Poisson-Vlasov equations. We solve these equations by sampling the phase space distribution function with discrete particles and calculate or approximate the mutual interaction of these particles. And what you see here is actually quite unusual. Usually you see a column density or what people are plotting. Here I plot each individual simulation particle of a rather low resolution simulation in light gray, and whatever is then dark here are essentially halos that are just like a gathering of many of these simulation particles. So this is one of the typical equations you encounter in computational astrophysics. Another one, in some degrees, the other extreme is an ideal fluid, where you have frequent collisions or microscopic collisions to be precise. And these collisions means that you can take moments of your collisional-Boltzmann equation and arrive at the Navier-Stokes, or in the absence of viscosity, at the Euler equations. If you take moments, this has the advantage that your dimensionality of your equation reduces from 6 to 3, and this means that using a grid on these three spatial dimensions becomes actually quite attractive. And in general, you can then, for each cell, assign a density, a single velocity component, velocity to the cell, and an energy density, and solve the equations of fluid dynamics on this grid. And one example where this is done here is why doesn't this start? A binary star where one of the stars is a giant star, and you get hydrodynamic interactions. Of course, there is gravity included in that simulation that triggers all these interactions. The distinguishing feature now of the Arepo code is how these hydrodynamic interactions are calculated. In particular, the grid on which these equations are calculated. In particular, what we have is a grid, but this grid is not, in general, reasonably arbitrary, meaning it does not need to be Cartesian as it is here. And the individual cells are, in principle, allowed to move wherever they want to. In practice, the velocity is given by the fluid flow, which gives you a Galilean invariance in your code. You would now say, okay, the Euler equations are obviously Galilean invariant. However, this is not the case for the discrete version on a fixed Cartesian grid. And there we come to the movement. In astrophysics, we have quite a lot of problems where we solve the internal dynamics of objects moving relative to each other. And for this, this kind of method has proven to be significantly superior to other approaches, in a sense that you need significantly fewer resolution elements, and the computational expense of calculating these grids is usually worth the effort. For most problems, not for all, I should say. So these are the main equations. Let me briefly mention some of the simulation projects that have been using this code over the last 10 years. I think the most visible ones, you might have heard a lot about them here already. The Illustris simulation, the newer version Illustris TNG, and the Auriga simulation, which is a cosmological zoom simulations of Milky Way-sized galaxies, so mostly in the area of galaxy formation. But I should also say that this is by no means the only project this code has been used. And here just a number or a small subset of simulation projects that this code has been used for. So my main point here is, like, from a software development point of view, this is an heroic effort of code testing, code optimization, and bug fixing of all kinds of different conditions that can occur in astrophysics. So all these simulations simulate different astrophysical systems. And by now this is reasonably well tested, which I think is quite crucial at a code of this complexity. So having this reasonably well tested code, we wanted to preserve this and make this available to the overall astrophysics, in particular to the simulation community, and really as a basis to run own simulations, also to develop further like problem-specific modules and run this on modern supercomputers. And as I said, very important, this needs to be a reliable code, have a clear license and clear terms of use, a clear literature reference, which is always a bit of a problem with a continuously evolving code. And it should be easy to get started with, and it was one of the main things that kept me busy the last couple of months, as well as well documented on a user and also on a developer level, meaning everything in the code should be explained somewhere in the code as well. So specifically, this means that this code is a fully MPI parallel code, which is not OpenMP parallel, I should say. I removed this functionality. Has a dynamic memory and workload balancing, which is very important for the cosmological simulations. Fully local time stepping, gravity in a 3PM method, which has been improved from previous code versions. So this is mainly all versions of Gadget that exist. Has this moving mesh hydrodynamic scheme. What I haven't mentioned yet has arbitrary refinement criteria. This means really you can actually refine on whatever criterion you want. Usually we use a master discretization, but this does not have to be like this. This comes with an MHD solver as well, and some rather simple prescriptions for cooling and star formation. These are rather meant as examples. They are not quite the state of the art in this sense. And what this also comes with for cosmological simulations is quite a neat feature, is a on-the-fly halo and sub-halo finder, which also orders the particle output, which becomes increasingly more important as the data output becomes significant and quite hard to manage to the analysis of it. And one key feature which is often a bit underappreciated is that the code is binary reproducible once you run it again with the same number of MPI ranks. Meaning this gives you the ability to really find really subtle bugs in your simulation code, also in really huge production runs. This also means whenever it doesn't appear anymore, that usually means that your machine is doing something wrong and not your code. This is quite neat to find this. Additional to that, and this is more than the work I've been doing, there is a user guide and a homepage for it, a documentation of all functions, which is important for future development, a release paper just to make clear what equations we are actually solving, for example, which also sometimes not too obvious reading simulation papers, and a lot of examples going from very simple code tests like just wave propagations all the way to cosmological zoom simulations, just to serve as examples how to get started with the code, and also have attached to them some simple analysis scripts just to exemplify how this is done. And one thing that I've introduced there also is that these examples are used for automatic code verification. That means whenever the code is changed or so, somewhere in Munich there is a computer running all these tests and checking whether this is actually still giving the same results or not. And we're using this not just in the public version, but also in the development version, which is where it's actually even more important. And last but not least, well, what we want this code to be is really a basis for other computational astrophysics, for other developers to be used. So yeah, this will be accessible in a normal Git repository, and we encourage people to extend this as well, have their own repositories, and ideally, if they want to make these extensions available, ideally via Git patches, and if they let us know, we can also try to check these patches, also if there are multiple of them, that they're not mutually exclusive, which would be quite important for the future. But all in all, this is supposed to stay a reasonably cleaned up code that everyone can use, and we plan to have this really as a long-term support version, but essentially just bug fixes through the code and no new developments in this version itself. And all this is going to be released soon, once I'm not talking about it, but actually doing something. Thank you.
You glossed over it very quickly because you're modest, but we saw a stamp of Deutsche the simulation result. Can you elaborate on that?
Yeah. So this stamp here was one of the stamps of a special edition of the German Postal Service that was science themed. So Gaia, I think, got one stamp, and among others also the illustrative simulation got one, which was of course made, like the people running these simulations, I wasn't part of it, like Volker, Lars and Mark Vogel were very happy that it's actually appreciated. It makes me very happy to see that the German society cares enough about our science.
Well, it also should make all of us happy, because theory is as important as observations, right? Gaia theoretical simulation got one.
Is it 145 euros?
145 cents.
Come on. So theory is not so valuable.
How much was Gaia?
I don't know.
Questions for Ryan? Go ahead.
What license is this?
That's a C. PhD.
And can you say a bit more about how the alternate processing works? What does that mean?
Okay, so what this essentially just means is, like, you have a script that can set up, run analysis on the simulation first, and the analysis means you need to have some reference, and you check whether this is within certain boundaries. So it's rather simple for things like let's say, shock or something like this, something that has an analytic solution where you can check against this. And this script then gives back, yeah, successful or not successful. Then you can obviously make your computer send you an email, okay, this was successful or this was not successful. And you can then do this arbitrarily complicated in terms of, we're doing this now, or we're trying to establish this now for every new code change that's done in the development branch, for example. Before it's actually merged, check whether all these code tests are successful or not. Did you break something or did you not? Or is this all fine? For the public version, it's like around 15 tests. For the development version, I think we are already at 20 to 30 and increasing. And we are going all the way to full physics. On my to-do list is to implement such a test for the TNG model for a very small simulation of this, just to check whether this comes out consistently with previous versions in this case.
Sure.
Who's going to answer everybody's questions?
That's
It's an issue when you release a code. Someone has to,
yes, large part will be me. Of course, I'm just a postdoc, so a large part will be Fortra, I guess, and Rudiger Packmeier, so staff scientists, MPA. Things that the three of us will mainly take care of this, try to take care of it. I hope to have written a significantly clear user guide.
Never works.
Okay.
Other questions? Well, let's thank Rainer again.
Hello, I'm Bekki Dawson, and I'm excited to talk to you about debris disk sculpting in multi-planet systems. This is a project led by graduate student DJ Dong in collaboration with me and postdocs Sarah Morrison and Andrew Shannon. So debris disk is a disk of leftover material from planet formation, like our solar system's Kuiper belt and asteroid belts. And just like Neptune affects the orbits of things in our Kuiper belt, like Pluto, exoplanets can sculpt the orbits of their debris disks. So here we're looking at a disk edge-on, where a planet on an inclined orbit is creating a warp in the disk. There have been a number of observed debris disk features that have been attributed to planets, including warps, rings, gaps, spirals, offsets, and asymmetries. And if you've seen a lot of these systems before, you'll notice that they're younger systems, and that's because the disk is still massive enough for us to be able to measure well. So one very useful thing that we can do is to use these debris disk features to infer properties about the young planets that could be difficult to discover otherwise. So here I'm showing a gallery of different simulations of different types of debris disk features by DJ. And for each of these features, we can use it to learn something about the planet that created the feature, like its mass or its orbit. And sometimes this works really well. So a while ago, there was a debris disk called Beta Pictoris, where a warp in the disk was detected, just like in the movie I showed on the title slide. And then some years later, a directly imaged planet was found in the system that had the properties consistent with creating this warp. And the warp provided an independent mass constraint on the planet, separate from how we usually infer it from the luminosity, which depends on planet formation models. But one challenge is that we're learning that many or maybe most planets reside in multi-planet systems, which leads us to sort of a planetary game of Clue, where we're trying to figure out which planet, or maybe a planet that we haven't even seen, is responsible for the warp. So on the left are the HR 8799 directly imaged planets, where in this system multiple planets are often detected. But a lot of times we're more in the case where we detect one planet and there may be other undetected planets in the system. And the properties of short period planets that we see on this plot of Kepler planet radius versus orbital period, where the color symbols are planets where multiple have been detected in the system, sort of inspire us that if outer planetary systems are like that, it's probably pretty common to have multiple planets there, even if we haven't detected more than one. So for Beta Pictoris, we showed a while back that the directly imaged planet must be the one responsible for the warp. Basically, it's such a dominant gravitational effect in the system that it would prevent some other planet from being responsible. But we have more of a cautionary tale with the debris ring called Fomalhaut, which has its center offset from the central star, so it's an elliptical ring. The interpretation was that that was sculpted by a planet on an elliptical orbit. And then in 2008, a planet was thought to be detected that would be consistent with that. But as the planet was studied more, both its orbit and other physical properties that show if it's a planet, it must be really low mass, told us that this planet was inconsistent with actually causing this offset. So there may be another undetected planet there causing it, and if we try to use this to learn about this detected planet, then we're going to be very much off about its properties. So DJ has been investigating for all these different types of debris-disk morphological features, whether undetected planets could cause significant errors in our inference, the properties of either a detected planet or a single planet that we posit to be there. I don't have time to discuss all of them, so I'm just going to show a couple of these features. So here we're looking down on like a ring of small bodies, and if we put a planet there, it will sculpt a gap in the ring. So this is the sculpting caused by a 3 Jupiter mass planet on a 16 AU orbit. This is a debris disk, it's not a gas disk, so it's basically creating a chaotic zone nearby it that evacuates out the planetesimals that are there. So that's the 3 Jupiter mass planet, but here's a configuration containing 2 planets that looks very similar. It's in orange, you can compare to the blue, and in this case, the detected planet B is only 1 Jupiter mass, and there's this undetected 1 Jupiter mass planet C that's closer in, maybe inside the inner working angle where it can't be detected. So if we were using this to infer properties of planet B, we'd be off by a factor of 3 in its mass. Fortunately, DJ has found that this problem only afflicts sort of a small part of parameter space. So this is a contour of the mass of planet C versus the semi-major axis of planet C for a particular planet B. And the blue shows how much our mass estimate of planet B, which is the detected planet, would be off. You can see there's only blue in a little small region of the plot where the undetected planet is pretty massive and near to the one that we detect. If the planet's further away or lower mass, then it's really the detected planet that's going to be dominating the gap. So we can be fairly confident that we haven't messed up its mass unless we got very unlucky. Here's another type of feature. This is a warp like I showed in the movie to begin with. And in blue is a warp caused by a single planet at 10 AU and its 15 Jupiter masses. And in black is a warp caused by 2 planets, one of which is at 10 AU and 1 Jupiter mass instead of 15, and the other is at 80 AU and it's 0.1 Jupiter masses, so that's probably going to be very hard to detect through direct imaging. And if we just look at the 2 warped features, they're fairly similar, and if we said, okay, we see a planet at 10 AU, it must be 15 Jupiter masses. If we were instead in the black case with that other planet, it's actually 1 Jupiter mass. So now we've got the mass wrong by a factor of 15. Again, though, luckily, DJ's finding that this is only a small part of parameter space that gets afflicted when we detect one of the planets. So now there's 3 different panels. I'm going to start actually with the one on your right. So this is mass of planet C versus semi-major axis. And the dot is the real properties of planet B. And then again, the blue means that we got it wrong. So there's only just this special strip that actually corresponds to their secular frequencies being similar at the location of the warp, where we'd be very wrong about planet B's mass. And that's like this sort of pathological case that I showed. However, if we dial down planet B's mass so that it's kind of barely detectable with direct imaging or not detectable, then there's a lot more degeneracy between what are that planet's properties versus what's going on with other undetected planets in the system. And there's a lot of blue on the left. We can be pretty off about whether it's one massive planet or 2 less massive ones. So DJ's been systematically investigating all these different types of features, and generally we come to the same conclusion for all of them, that usually the prime suspect is the culprit. So it's a cliche that the butler did it, but probably he did. And that leads us to summarize that we can infer young planets' properties from sculpted features of debris disks, including warps, gaps, offsets, thickenings, and asymmetry. In multi-planet systems, usually a single planet is the one that dominates the sculpting. So that's good for using these sculpted features to infer the planet properties. In particular, when the suspect is massive and far away enough to be direct imaged, our inferences are only in air for sort of a special, finely tuned part of parameter space. So in particular, if we had a big sample of planets, we're not going to be really wrong about the typical properties. There are some caveats in special cases, so stay tuned for DJ's paper where she goes through each of these features in detail to say when you should worry and when you should not. Thank you.
You assume the planets are coplanar, but what if there is some inclination relative to the disk of where the imprint is being left? So then you have more uncertainty, I guess, as to an intruder.
Yeah, and so the uncertainty, and if there is an undetected planet, what's its mutual inclination, can come into play in these sort of pathological cases, but it still tends to be like the big features where being inclined makes a difference, or the warp feature that I showed, and then also it turns out the spiral, and then the thickening, the vertical thickening of the disk. And it still turns out to be more of a mass effect in terms of what's gravitationally dominating. So even if the other planet has a fairly inclined orbit, it's not, if it's not massive enough to be a big player gravitationally, then it's not such a worrisome case. But yes, definitely if we want to do a full 2-planet model, we want to take into account the full 3D orbit, particularly for some of these features that are created by being mutually inclined with your disk.
You say that most often it's one planet that dominates the sculpting. Is that because in multi-planet systems, usually one is much more massive than the others?
It doesn't necessarily have to be, which is good because there's, at least for short period planets, there's emerging evidence that planets within a system tend to be similar to each other. So we wouldn't want to have to assume that. So it's often a combination of the mass and semi-major axis, and that's why I'm saying it's kind of fine-tuned. It's like not only for the other planet to be important, not only does it have to be like exactly the right mass, but it has to be a particular semi-major axis to go with that mass, like as you can see in, it's coming up. But you basically, in the parameter space of mass and semi-major axis, you see like a line. So that then it starts to be fine-tuned that your other planet would just happen to lie along that line. Now for the case with the nearby planet, with creating the gap, that's maybe less fine-tuned in that this is a fairly similar mass planet to the one that's detected, but then it's sort of uncomfortably close to, I didn't say what this is, this dash thing is where the other planet would be unstable. So then it's also in some sense kind of in a special place where it's like just about to be unstable, and it has to be exactly right there. So I think ultimately we want to try to synthesize, like, given how similar different planets are in different planetary systems, how is this going to affect the results? But it doesn't, the one planet being most important doesn't necessarily assume that the other planets have much lower masses.
Any other questions?
I have a question about timescales. These fine particles that give rise to these debris disks are thought to be the result of collisions between, asteroid-sized bodies.
Yes.
If a collision occurs between a body in a circular orbit and one in an elliptical orbit, you could imagine that the debris from that collision might not instantly be circular and would induce structure just as a result of that collision. About how much time does it take for that sort of collision-induced orbital anomaly to damp out and the planetary effect to dominate?
It depends on what type of feature we're talking about. Like these particles lie on like what's called the force plane, and any sort of dissipative process in the system would damp things to that plane, including collisions in general. So really what we have to do, these simulations that I've shown are all the planetesimals. They're not actually the dust that we would see. So we have to take each planetesimal and sort of generate a distribution of dust. And an even more important effect than the collisions is the fact that they're small and subject to radiation pressure, particularly in the optical images, and then see what it looks like. But the good thing is that, like, even though, as you say, there's indeed sort of a distribution of random velocities that's being produced by the collision, here there's sort of like this maximum height that's like, this is the planetesimal, and even if it got a bit damped during the collision, there'll sort of be things all the way down from here. So still measuring the height and location is reasonable, even though we're actually seeing the collision products rather than directly seeing the planetesimals. That being said, it's one nice advantage of using all our other longer wavelength observing capability is that we have to worry at least less about the radiation pressure. We're more directly seeing the parent bodies that we're simulating here instead of just the dust produced. But to do a direct comparison with any of these actual images, then we usually take the simulations and sort of post-process them to include radiation effects and a collisional cascade and all those things.
Well, we all look forward to your colloquium later today, and let's thank Bekki again.
Okay, great. Well, this morning I spoke about the interior structure and evolution modeling that my group and I are doing. And in my presentation here at lunch, I'd like to describe an aspect of some of the planet population statistics that we've been working on. And so this is a project led by my grad student, Andrew Neal. And we've been working towards a joint 3D mass radius period distribution of close-in exoplanets. So at this point, statistical studies of exoplanet populations is a whole sub-industry in the exoplanet field. In transit surveys, there have been multiple studies probing the radius period and joint radius period distributions. This whole slide is woefully incomplete. The slides would go way into the basement if I put a figure from every relevant paper. Radial velocity surveys, of course, give you constraints on the period and mass distributions of planets. And then by combining radial velocities, transits, and transit timing variations, there have been studies of the mass radius distributions of planets in the mass radius plane. But many of these have looked at either the distribution of planet masses conditioned on radii or the distribution of radii conditioned on masses. And so Andrew and I have endeavored to take steps towards a 3D joint mass radius orbital period distribution of planets. And to do this, we've been applying kind of a hierarchical Bayesian modeling technique, essentially combining the approach that's been used by Dan Forbin-Mackey and collaborators and Chris Burke in a standard paper constraining the occurrence rates from Kepler, but extending their approach, the hierarchical modeling approach that's been used to characterize the radius period distribution of Kepler planets, to add an additional dimension of masses when the masses are available. Now, the sample of planets that we're using in this effort is a sample of Kepler transiting planet candidates with radial velocity follow-up. So that's a sample that all the results I'm going to be presenting today are based on. And so we're using essentially the same host star properties and cuts as Fulton and Pettigrew. So this is based on Kepler data release 25. And they're focusing in particular on the brightest host stars and planet candidates, for which they got high resolution spectra using Keck high-res. And those combined with Gaia parallaxes give median planet radius uncertainties of less than 5%. In our sample, we're focusing on planets with orbital periods shorter than 100 days. And in this kind of clean sample of Kepler planet candidates with well-characterized host stars amounts to about a bit over 1,200 planet candidates. And now roughly 60 of those have some radial velocity mass constraints that we're folding into our analysis when available. And so in what I'll present today, I'll show results with a suite of parameterized models. And essentially, we consider a variety of models parameterizing the joint mass radius period distribution, each of successively increasing complexity. And so our goal is to offer a menu of options to anyone who would like to use this work, either to make predictions of planet masses, to extrapolate to get eta sub Earth, to project to get marginal distributions. You'll have a menu of model options so that you can assess the robustness of your results to the choice of model and model misspecification. So the first, simplest model that we explored includes a single planet population. And here, essentially, we're taking the broken power law distribution for planet orbital periods, combined with a parameterized mass distribution, and then combining it with a broken power law, probabilistic power law, mass radius relationship, similar to those exoplanetologists in the audience, similar to the one applied by Chen and Kipping. Now, in this plot, essentially the black points and histograms represent the raw data. So these are the 60-odd planets for which we have radial velocity mass measurements. This is a histogram of planet radius. So the black shows the raw distribution of the sample, not corrected for incompleteness. Whereas the blue is our retrieved distribution for the underlying population. The upper left shows the mass distribution, essentially showing kind of telling you how common planets are across this diagram in this dimension for masses. Again, with the blue showing our retrieval for the underlying population, and the black, the observed, the histogram of the Kepler masses, and then the upper right-hand corner is the period distribution. Okay. However, from observations of a bimodal radius distribution in the Kepler sample, we have good reason to expect that there's not just a single subpopulation of planets, but rather potentially multiple populations. And so in our second model, which includes two mixture components, we allow for the possibility of evaporated cores. So we consider a population of planets that again follows a broken power law mass radius, probabilistic mass radius relationship, representing planets that have gaseous envelopes. But then evaluating their mass loss timescale or envelope loss timescale, we assign them a probability of having either retained or entirely lost their envelope. And if they've lost it, then we instead define their radii for their retrieved mass by a model mass radius relationship for rocky planets. And so in this work, since we have a limited number of planet mass radius measurements, we're not actually trying to retrieve the mass radius relationship for rocky planets, but we use it as to specify the radii at a given mass for our rocky cores. So in this context, we have a population of planets that kind of all the planets we're considering started with primordial envelopes, but then some subpopulation lost them to photoevaporation, and now just their remnant rocky cores are left. We may also be curious whether there's a separate population of rocky planets that just intrinsically formed as native rocky planets that never accreted primordial envelopes and aren't tied to the gaseous planet population really in any way. And so in our third model, we included a third component of intrinsically rocky planets for which the period and mass distributions aren't based upon that of the gaseous planet population. And so the intrinsically rocky planet population is shown here in green. And we do retrieve an occurrence rate in that intrinsically rocky planet population that is inconsistent with 0. And finally, we explore adding a second, a bit more complexity in the mass distribution of our gaseous planet population, allowing for not just a single log normal distribution, but a mixture of normals to give the model a bit more flexibility in that realm. And so in this case, so I've shown a suite of 4 models. The first is a single planet population, which is kind of similar to what the analyses that have been done to date. The second allows for a population of planets that retain their envelopes and a population of planets with evaporated cores. The third adds an additional population of planets that intrinsically formed rocky. And And each of those populations are also included in this fourth model with an additional flexibility in the mass distribution modeled. And I'll just sum up by saying that by comparing, doing detailed model selection, we see that models 2, 3, and 4 are strongly preferred to this single component model. And actually models 3 and 4 that include the intrinsically rocky population are preferred as well over model 2 that does not include it. While there is no statistically significant preference of model 4 compared to model 3. And as a parting note, I'll just point out, kind of motivating our desire to show a menu of options of models, that the extrapolated eta Earth values that you get using this suite of models are highly model dependent. And in particular, when you include within the models the possibility of the subpopulation of evaporated cores and intrinsically rocky populations, the estimates for the occurrence rate of rocky planets out at 1 AU around G-type stars drop significantly. So, thank you.
Leslie, how do you account for selection, observational selection effects? Because some of the parameter space is not easily detectable.
Right. So, I mean, this is following a similar approach as the previous analyses of the Kepler radius period distribution. So, Jesse Christensen and others have done detailed injection and recovery tests to characterize the completeness of the Kepler sample to non-detected planets. And so that's folded in to our inhomogeneous Poisson process likelihood for kind of the radius period distribution of Kepler planets.
Indo and then Ramesh.
Yeah, so my question was similar, but relating specifically to the masses. Do you know that the 60 objects for which you have masses are not somehow preferentially introducing some correlation, that the mass determinations are really independent?
That the mass determinations are independent of
the radius and the period?
Well, so certainly there are biases in the radial velocity follow-up, and there may also be biases in studies of transit timing variations, mass constraints, and so ultimately one would want to include both in a more complete analysis. In this case, given that the planets were selected for radial velocity follow-up with no prior knowledge of their masses, just based on the radii and orbital period and kind of post-star properties that were known at the time, we've gone through carefully to show that that selection process isn't actually biasing our results beyond what you would expect just from the fact that the radial velocity masses are measuring kind of short period planets. I'm not sure if I fully addressed your...
Yeah, I mean, it wasn't clear how many cases there were radial velocity measurements, but they failed to produce a mass, and if that...
So those are at least the cases that are published are included in this. Yeah, so one of the benefits of the radial velocity follow-up effort of the Keck, using Keck high-res, the radial velocity follow-up of Kepler targets, is that they didn't just publish their detections where they got some like 3 sigma detection of the planet's mass, but they also published kind of upper limits in cases where they didn't have a statistically significant detection. And so those are also folded in here.
Ramesh?
So I noticed that there were 2 ultra-dense planets near the bottom of your plots, which didn't fit any of your models. These 2 guys down there.
Yeah, I think those are some of those. Those are some of those upper limits. Those are the upper limits. They also have very. I mean, I think these error bars were derived on a linear scale, and now I'm plotting them on a log scale. But these are consistent with the non-detection. So these are actually radial velocity upper limits.
So you would say that they are really very low mass?
Yes.
Below 1 solar mass?
Yeah, these are kind of planets in multi-planet systems that were kind of carried along for the ride when other larger planets dictated the selection of that target for radial velocity follow-up. And so they're detected in transit, so they're included in the radial velocity fit when fitting the radial velocities to the multi-planet systems. So there is some posterior distribution derived for their masses and some upper limits placed on their masses, but those upper limits aren't physically constraining.
Okay, we need to move on. Let's thank Leslie again.
Can you hear me okay? Yeah? Yes? No? Better? 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 Okay, great, thanks. So my name is Trevor. I'm working in the group of Tim Kaxiris, and I'll be talking about the machine learning study of two-dimensional magnetic materials, a little bit changing the topic of research. It's really a pleasure to be here. Thank you so much for having me. So the goal of this, in part, is to look at materials discovery. Materials are driving scientific and industrial innovation. For instance, we need light, yet durable metals for building aircraft. We also need to have light and heat-resistant engines in cars to reduce or improve fuel efficiency. We also need to have exciting things like really strong magnets to have levitating trains. And also, perhaps one day we'll have wires in our power lines that are carrying current with zero dissipation of energy or zero resistance through superconducting wires. And also, we're interested in having these things for data storage and interested in having new magnetic materials for applications in data storage and things like spintronics, which is, you could say naively, electronics that has higher energy efficiency. So I'll talk about materials discovery, and I'll ask, why do we need to search for new materials if we already have things like experiments and computer simulations that already exist and do a pretty good job? Well, I'll argue that the space of materials is huge. There are over 50 million known molecules and crystal structures, and this is not counting the ones we don't know about. And I propose machine learning as a path towards materials discovery. What is machine learning? Well, it's like teaching computers to understand patterns and make predictions. The Linux guy knows everything. He's answering the question. Okay. What about machine learning and materials discovery? Well, the idea is you want to use machine learning to approximate some function f of x, which maps the crystal structure to a property. And you do that by taking some data and some algorithm to create this function f of x. Now, the idea is recognizing patterns in data, and I'll go through some simple example of how we do that every day. So imagine that you're a Greek alchemist living in ancient Greece, and you found a small set of random elements. You have iron, helium, hydrogen, air, fire, water, and earth, and you know a few things about them. You know their atomic number, and you know their color. For instance, everyone knows that hydrogen is blue and lithium is red. So you want to understand more about these data, maybe figure out if there are more chemical elements that exist. And so you ask yourself, what is a good descriptor? And what are the trends in my data? Because you're Plato, you choose the atomic number as a descriptor, and your algorithm is sorting these in terms of increasing order. So if you do that, you find the following: helium, hydrogen, helium, lithium, air, fire, water, earth, beryllium, and so on. And you notice that you're going up in increments of 1 atomic number. And if you recognize this trend, you find that air, fire, water, earth, maybe they aren't atomic elements. And you find that there's something missing between 6 and 8. Are there any chemists in the audience? Can you tell me what this is? Nitrogen, yes. That's exactly right. So if you continue along these lines, eventually you have the entire periodic table. Now, we've done this for chemical elements. It's something familiar to you, and you know the trends that emerge in the periodic table if you go along the columns and the rows. Can we do something similar for crystal structures? Now, this is diamond. This is the crystal structure for diamond. And there's one person here that knows that the color from this diamond is due to this defect in diamond. So we have this crystal structure. A lattice of diamond is mostly carbon atoms, but there's sometimes defects. You can replace one carbon with nitrogen, and neighboring site is vacant, and this defect produces this red color. So there's this link between the structure of diamond and its property, in this case, defect and the color. And we learn structure-property relationships using machine learning is the question. Now, my goal is to do a similar study, or use this framework for understanding 2D magnetic materials. And I'll do this by trying to predict something that we want to know, like the magnetic moment, which is parameterizing the degree of magnetization of a material, and take as inputs into some function approximated by machine learning things that we already know, we can get from the periodic table, like the number of spin-up electrons for an atom. This is a non-traditional way of studying 2D magnetic materials. Okay, so the material that we'll look at to apply these machine learning tools is a class of transition metal trichalcogenides. Most popular is chromium germanium telluride. The chromium atoms sit on these A sites, the germanium atoms sit on the B sites, and the tellurium atoms sit on the X sites. And this is a 2D material. That means if you have like a graphite, you can cleave off one atomic layer of carbon atoms known as graphene, and these are a class of two-dimensional or layered or van der Waals materials. Chromium silicon telluride is another of these 2D materials, and it turns out that chromium germanium telluride is ferromagnetic. That means all the spins at the chromium sites align, pointing in the same direction, but chromium silicon telluride happens to be anti-ferromagnetic. So by changing one atom, germanium, to silicon, these are both non-magnetic atoms, you can still change magnetic order. So by changing the structure of your material, you can change its properties. So I thought, well, how can you? Oh, this is, by the way, through theory. These are just simulations. So I thought, how can you really exploit this? How much can you change the property of something by changing its composition? So I created 200 of these ABX3 structures, and if you were to tune the atomic composition ad nauseum, you'd get about 10 to the 4 different combinations. I just stuck with 200 because of computational constraints. I looked at different magnetic configurations, anti-ferromagnetic and ferromagnetic, and extracted things like formation energy and the magnetic moment. And I'll focus on just on the magnetic moment, which is the degree of how magnetized, how much something can become magnetized. To give you an idea, I would take this structure and replace at these sites different atoms coming from these regions of the periodic table. If you do this, you get about 200 structures, or 198. So then I would calculate using a density functional theory, which is a computer quantum mechanical simulations to predict the properties of materials. And I get the following, where this is structure is for tellurium at the X site, for selenium at the X site, for sulfur at the X site. The vertical axis is an A site substitution with these transition metals, and the horizontal axis are the B site substitutions with these atoms. And the color is a magnetic moment. So the darker the color is the stronger the magnetic moment. And original structure, chromium germanium telluride, is here. And you find that if you look across this grid, you have other structures which have even higher magnetic moment. and that's good. We want a higher magnetic moment. The other thing you notice that there's this interesting pattern in these data. You can see as you shoot from tellurium to selenium to sulfur. So the hope is to ask a statistical model or machine learning model to learn the trends in these data, to be able to exploit them for predicting something quantitative, or the magnetic moment in this particular case. So how can we do this? Well, we use a machine learning model. It can be something as similar as linear regression, fitting mx plus c, fitting a line to some, fitting a points to some line. In this case, I'll give a different example, maybe less familiar, the random forest model based on these decision trees. And the idea is that we have inputs, things like number of spin-up electrons. We want to predict the magnetic moment, something that's hard to calculate, hard to measure. We train our model on some data. We make sure it's working well using test data, and we can tune the parameters of the model by taking the mean absolute error of the guesses of what the output are at some nodes with the observations between some regions. So if we build a model and it works fairly well, we can then try to predict the magnetic moment from our DFT simulations. And if we do that, we get the following. This is not a line fit. This is kind of a parity plot with or quantum stimulated magnetic moment on the x-axis, and a machine learning predicted magnetic moment on the y-axis. And this dashed line is a guide to the eye, with training data, the green circles, and the test data, the red squares. And because all these points fall pretty close to that line, which is a line of perfect prediction, we can tell that our model is performing pretty well. So now we have a model trained on 200 data points. We can then try to predict many, many more points very quickly. So we apply this model to over 4,000 structures, and we do some kind of screening mechanism, or have a screening approach where we pick only machine learning predicted structures that have a certain magnetic moment. We can also choose other screening criteria, such as chemical stability, which I didn't explain, but we can do it. And if we do that, we end up with some candidates for new 2D magnetic materials, which we can then verify by DFT and eventually synthesize to really show that they can exist and they have the properties that we want them to have. So perhaps materials discovery of the future is a scheme where you ask not Alexa, but Atoma, please make me some exciting new hard drive that has even more space than I have now. Or perhaps make me some new efficient LED, a light bulb with even greater efficiency. Or perhaps some solar cell to save the environment that has even higher efficiency than we have today. Thank you. I agree. So if we had infinite knowledge and perhaps perfect models, we might not need physics. But how this really works is we need to know a lot of physics in order to make things work. It's an essential ingredient. So it's not replacing physics. It's maybe aiding the physicists. And like you make have some points on a line, you make a linear fit. This is in a sense machine learning, and it's you need to know what is the x and what is y, the meaning of m and c in this case. So that's absolutely right. We need to know a lot of physics in order to make sense of the output of the model and what it's predicting. No. There's no fear of that happening. Don't worry.
So you were comparing your AI predictions versus density function theory.
That's right.
Predictions, right? So my question is, how well does density functional theory itself do when you compare its calculations with the real material in the lab? How good a correlation would that plot be?
That's a good question. So it performs well for some things, and it fails for other things. And for magnetic moment, it often, or for magnetic properties, depending on the material, there's some difficulties in getting it to degree with experiments. So I can say that down to 2 layers of this chromium germanium telluride, we have experiments that confirm that it's magnetic. Down to 1 layer, no one has a chance to measure it yet, so you can't know for sure if it's actually correct. But there are other examples of chromium triiodide where down to 1 layer, the DFT says it should be magnetic, and the experiments show that it's magnetic. So there are some successes, and there are some failures, or some things that aren't certain. So DFT isn't the proof, so it's more of a guide. So if you have some result, then you should try to do perhaps more DFT calculations than I've done, and then the real test is to actually synthesize it. Thank you. Thank you.
That's very nice. Thank you.
Thank you. My pleasure.
It's interesting that you can get away with so few data points.
Yeah, it's actually
compared to some neural network thing.
pretty surprising. If you well, I made it like this. So I had a fixed crystal structure, and I would go maybe not too far away. So in that close space, you can kind of interpolate a bit. But interpolation means you're still scanning over like 4,000 different structures, and so it somehow still gives you something.
We really would like to
Get to know better. That's nice. Nick Wrangler and I have been learning a little. Well, Nick has been learning a lot of neural network work, and I've been learning a little. And they haven't really helped us as much as we hoped. For reasons that would make Avi nod his head. It seems like we don't have enough data. We really need to put more physics in. And so we end up using Gaussian processes where we can inject some more physics. But I kind of wonder if we should maybe go learn about decision trees around the forest.
Yeah, I tried doing some things work better than others. I think I tried this on Gaussian process. It didn't work for some reason. I didn't spend a huge amount of time tuning like random forest pretty well really quickly.
I would like to see, for instance, how that Kelvin
and it's not perfect, but you get an idea from physics. I didn't show it, but you know that the feature
so different people have different,
It tells you some maybe why which descriptors are more important than others. It gives you an idea of why is this doing what it is, why is